Hello everyone, I'm Meng from Nanjing University. Today I'm delighted to share Pyrrha with you, which is focused on managing transient congestion using scalable and head-of-line blocking-free flow control. Due to visa issues, the two co-first authors could not be here in person today, so I am presenting on their behalf. To clarify, I'm not one of the authors of this paper, so please understand if there are any parts I explain unclearly. First, let me provide some background information. With data center networks evolving, there are three trends making congestion control increasingly struggle to manage transient congestion. The first trend is that as port bandwidth grows, more and more flows can be sent out in the first RTT. Since most congestion controls require one RTT to receive the congestion signal, they cannot manage the transient congestion caused by the first RTT traffic. The second trend is that the increasing scale of data center networks and the emergence of workloads such as distributed training will result in more bursty traffic, which means more transient congestion. The third trend that makes the situation worse is the decreasing buffer-to-bandwidth ratio, which significantly reduces switches' ability to absorb transient congestion. These three trends together demand that data center networks should have an enhanced ability to manage transient congestion more quickly. So our vision is to leverage per-hop flow control to handle transient congestion. When applying per-hop flow control, a switch can manage congestion using control frames within one hop transmission delay, which means around 1 microsecond. And the traditional congestion control could be used to adjust flow rates at the end host to avoid persistent congestion. This labor division between congestion control and per-hop flow control leverages their unique positions to collaboratively manage data center congestion. We will later demonstrate the effectiveness of this division. Next, let's explore the drawbacks of existing per-hop flow controls. Naive flow control like PFC is widely used to avoid buffer overflow in the Rocky V2 network. However, PFC is well known for incurring head-of-line blocking, a performance killer in Rocky V2. Let's use the scenario shown on the screen as an example to introduce head-of-line blocking in detail. In this scenario, multiple congested flows intersect at port P2, causing congestion and trigger PFC to ports P3 and P4. Let's assume another vulnerable flow share the same queue with the congested flow on P3 and then passes P1. Although this flow does not pass the congested port and allowing it to send will not cause buffer overflow, it will also be paused innocently, which is called head-of-line blocking. To demonstrate the impact of head-of-line blocking on performance, we conduct a simulation in a factory topology. The test workload consists of three types of flows. Incast flows start at the beginning of the simulation, in which all other hosts send small flows to the last host in the topology, making the last port congested. Vulnerable flows are flows sent from other ports to other hosts in the last ports, with the total rate being 80 gigabits per second. These flows may suffer from head-of-line blocking at destination aggregation switches and core switches. And background flows are sent between uncongested ports with the total rate being 80 gigabits per second. These flows could also be blocked if congestion is not properly controlled and spread to other ports. The result of PFC is shown on the screen. During the first 2 microseconds, vulnerable flows are significantly blocked. Between the first and second microsecond, congestion spread to all of the ports, blocking background flows. This result reveals that head-of-line blocking incurred by PFC significantly impacted the transmission of uncongested flows. Additionally, CBFC performs similar to PFC, as they both control transmission at the granularity of the entire queue. To overcome the head-of-line blocking caused by coarse-grained control, an idealized way is per-flow queue flow control, where only queues assigned to congested flows are paused and uncongested flows are unaffected. However, this solution is not scalable as there could be thousands of flows observed on a port. BFC, the state-of-the-art flow control, attempts to mimic per-flow queue using a limited number of queues. When the number of active flows exceeds the number of queues, the remaining flows are randomly assigned to the already used queues. As shown in the figure, although many uncongested flows complete quickly, some flows take a long time because they randomly share queues with congested flows and suffer from head-of-line blocking. Given this situation, we raise the question, how to eliminate head-of-line blocking caused by flow control in the most cost-effective way. Reviewing existing per-hop flow control protocols, we find the key is control granularity. A coarse control granularity can lead to head-of-line blocking, while overly fine granularity can result in excessive resource consumption, making it not scalable. Therefore, we need to find a better control granularity. Our analysis begins with the congestion in per-hop flow control, which is illustrated through this example. In the example, 5 flows intersect at P2, causing congestion, which then triggers pause to P3, P4, and P5. As flows continue to transmit, the queue length at P3, P4, and P5 increase, leading to pause to upstream ports. Analyzing the port involved in this congestion event, we find that they naturally form a tree structure. Only the congestion at P2 is unavoidable, and the congestion at other ports is triggered by pauses from P2. Therefore, P2 is the root of both the tree structure and the congestion, which we refer to as the congestion root. Since the congestion root is the root cause of congestion, the flows contributing to it form the minimal set that must be controlled. By only controlling these flows, other flows will not be blocked. And the number of concurrent congestion routes observed on each port is moderate. Therefore, only a reasonably small amount of resources is required at each port, making the flow control scalable. According to our analysis, we conclude the key insight of this work. Congestion root is the appropriate granularity of flow control to achieve both blocking-free and scalable. Based on this insight, we propose Pyrrha, a congestion-root-based per-hop flow control protocol. Specifically, the Pyrrha switch will embed the congestion root ID in the pause frame. Upon receiving a pause frame, the upstream Pyrrha switch allocates an isolation queue dedicated to the congestion root. Then traffic passing through the congestion root is placed into the isolation queue. Traffic that does not pass through the congestion root remains unaffected by the congestion. By leveraging congestion root as the control granularity, Pyrrha can be formally proven as a head-of-line blocking-free flow control protocol requiring minimal queues. Please see the technical report released together with our paper for the formal proof. However, to realize congestion root-based flow control, there are some challenges to be solved. The first challenge, as well as the key challenge, is identifying the congestion root accurately. This is difficult in practice because upstream non-root hotspot can become congested before the actual congestion root. For example, non-root port P3 might be congested first, and port flows passing through it. However, the true congested root is P2. If Pyrrha cannot converge to recognize P2 as a root, it can cause head-of-line blocking for the vulnerable flow that does not pass through P2. Inspired by the spanning tree protocol, Pyrrha proposed a distributed congestion root election mechanism. This approach is based on the fact that congestion roots are always downstream, which ensures accurate root identification. We use the following example to illustrate the process of distributed root election. When there is no congestion, all flows are enqueued into the port's output queue. If the output queue length exceeds the congestion threshold, the port claims itself as the root and sends the port frames upstream with its port ID. Upon receiving the port frame, the upstream port assigns an IQ dedicated to the congestion root and enqueues the flow passing through the congestion root into the IQ. When the downstream port P2 also experiences congestion, it identifies itself as the congestion root and sends the POSIX frame with its ID to the upstream ports. Upon receiving this port frame, the upstream port P3 relinquishes and recognizes P5 as a new congestion root. After a new root is elected, Pyrrha merges the old congestion tree into the new one. This process is achieved by sending merge frames from the false positive root P3 to upstream ports. When P6 receives the merge frame, it cancels the IQ assigned to P3, allowing the vulnerable flow to be free of the blocking. After actual congestion root arises, the congestion root election and the merge process finish within several link delays. Therefore, false positive congestion roots have a minimal impact on performance. The second challenge is identifying congested flows. Pyrrha actively identifies and controls congested flows rather than passively reacting after they reach the congestion root. This approach prevents additional pressure from being placed on the congestion root by new flows. To determine whether a flow will pass through the congestion root, the Pyrrha switch needs to identify the onward path of each flow. This is challenging as various load balancing protocols may be applied in Datacenter, which can complicate determining the path of packets. The third challenge is handling tree tangling scenarios. Several concurrent congestion trees can be intertwined among themselves. As an example, after a congestion tree forms with P2 as a root, two additional flows from P8 and P9 are sent to P6 and then passes through P3. The new flows, which are not part of the congestion tree rooted at P2, will cause P6 OQ congestion, prompting P6 to declare itself the root and deposit these flows. In this case, two congestion trees tagged with each other, posing challenges for the flow control mechanisms. For reasons of time, we omit Pyrrha's design on the last two challenges. Please see our paper for details. Pyrrha is implementable. We implement a Pyrrha prototype on Tofino 2. With careful optimization, it requires only 40% of Tofino 2 memory resources to support around 10,000 hosts. We tested the performance of Pyrrha prototype in a two-stage closed topology where all switches are running Pyrrha. Under both web server and web search workloads, Pyrrha significantly reduced the FCT compared with PFC. Next, we show some simulation results. On the 160 host topology, compared with other flow controls, Pyrrha improves the performance of vulnerable and background flows significantly without compromising the performance of congested flows. Compared with a pure congestion control solution, Pyrrha also significantly benefits vulnerable and background traffic without compromising congested flows. When Pyrrha cooperates with congestion control, the performance of small flows is further improved. We also investigate the worst-case queue usage of Pyrrha. Even under the most stressful workload, Pyrrha's queue usage is under 20, which is moderate. Finally, let me make a conclusion. Pyrrha is a congestion-root-based per-hop flow control protocol which can control the flow transmission at a fine granularity without head-of-line blocking while requiring only a minimal set of queues. Through Pyrrha, we demonstrate that a head-of-line blocking-free yet scalable flow control is feasible. We believe that it's time to embrace per-hop flow control to react to congestion promptly. Thanks for your listening.